We'll begin our course by ignoring all the little details that will consume us later and just talking about some of the big ideas of statistics. What's it all about? So first of all, statistics is the art and science of turning data into knowledge. Data is trying to tell us a story, and statistics is about learning how to hear the story the data is trying to tell. It's important to begin with the idea that data is better than anecdotes. Maybe your Uncle Ralph was a lifelong smoker and lived till he was 95 when he died while hang gliding. It doesn't mean that smoking is not dangerous. It just means that Uncle Ralph didn't die of smoking. In fact, the data tells us that smokers are 25 times as likely to develop lung cancer as non-smokers. About 20% of all deaths, 1/5 of all deaths in the United States, are related to smoking. That's pretty astonishing. So to say that smoking is very dangerous doesn't mean everybody dies of smoking who smokes. It means that they're much more likely to die of lung cancer or some other cause related to smoking. So that's one important idea. Data is important. It's better than a story, an anecdote. Another big idea is that variation is everywhere. Much of what this course is about is to use mathematical tools to understand random variation. One way we do that is with visualization. Simple graphical tools can tell us a lot. Interesting, important stories quickly and easily. Here's an example. This is real data from houses for sale in Fitchburg, Wisconsin a few years ago. And let's see if we can read what this says. Down here on the horizontal, the x-axis, we have the total finished square feet of the house. And up here we have the price, how much people were asking for it. So 6,000 square feet. This house was about 6,000 square feet. And the owner was asking $750,000 for it right here. And we see, unsurprisingly enough, this tells us, sure, there's random variation. The sizes of the houses vary. The prices vary. But those two variables are related to each other. Not a big surprise. The bigger the house, as you move from right to left to right, the more expensive it is, in general. And notice this particular graph also separates the houses that have wood-burning fireplaces from those that don't. So it lets us compare those two. So this simple picture tells us a whole lot about the houses that were for sale in Fitchburg, their size and how much they were asking for them. Also very important when we talk about data, which is numbers, that a few numerical summaries can help us understand quantitative data quickly and easily. So quantitative data, just data that's numbers. So we're going to become familiar with the mean and the median. Those are both two ways of measuring the average, what happens on average. The standard deviation and the interquartile range are both ways of measuring how spread out the data is. Are all the numbers really close together, or are they spread way out? And the 5-number summary includes both of those things. So just a handful of numerical measures and a few numerical summaries can help us quite easily understand a lot about quantitative data. Another important idea is the importance of the baseline when you're talking about increased risk. So when you talk about something increasing the risk, you need to know what the baseline is. So a few years ago, it came out that bacon and other processed meats were classified as carcinogenic. Bacon increased the risk of colon cancer by 18%. That sounds pretty scary. But increased by 18% from what to what? Well, it turns out it was only an increase of lifetime increased risk of lung cancer from 5.6% to 6.6%. Excuse me, not lung cancer, colon cancer. So yeah, the risk of colon cancer went up, but if you don't do anything, it's 5.6%, and if you eat bacon, it goes up to 6.6%. And that's eating 2 pieces of bacon every single day. It's just not enough to make me give up my occasional pieces of bacon. And here's a link to the details of this story. So when you talk about something increasing the risk, making things riskier, you have to know where you started. Representative samples. There's another big idea in statistics. Even a very small sample, if it's representative, can give information about a population in the millions. Population doesn't necessarily mean people, by the way, it just means the large group you're interested in. So if you have a representative sample of houses for sale in New York City, then you can learn a lot about all of the houses in New York City. And much of what we do in the last half of this course will be using small samples to understand large data sets, large populations. This is what inferential statistics is about, drawing a conclusion about a large group based on a representative sample. And the opposite of that is that unrepresentative samples are junk. If the sample is biased, just forget about it. It's worthless. So if we surveyed every single Edgewood College student and then tried to use that to draw conclusions about all college students in the country, it would be horrible use of statistics. Edgewood College students are not a representative sample of all the college students in the country. So even though there are 2,500 Edgewood College students, it just makes no sense to try to say something about all college students based on that. It's not a representative sample. Association does not imply causation. This is one of the most important ideas I want you to leave this course with. As an example, as ice cream sales increase over the course of a year, so do deaths by drowning. Does that mean that ice cream causes drowning? Well, no, probably not. What's going on? What's going on is that ice cream sales increase in the hot summer months, and that's when people are swimming outdoors and drowning. So ice cream doesn't cause drowning, and people drowning doesn't cause ice cream sales to go up. They're both caused by hot weather. So if you want to show a cause and effect relationship, association alone, if that's all you have, must be treated with extreme caution. Look for other examples of this. Google association does not imply causation and see what kind of interesting examples you can come up with. Now, often there is causation and we want to find evidence for it. And we'll see that the best way of demonstrating cause and effect, when you can do it, is a randomized controlled experiment. Randomized so that you're just randomly associating subjects to different groups. Controlled, you need to have a control group, and that's what an experiment is. And we'll learn more about that later in the course. Another very important idea, statistical significance does not imply practical significance or practical importance. So, at least in one study, over-the-counter sleep aids help insomniacs fall asleep faster. So there's statistical evidence that if someone has trouble falling asleep, the over-the-counter non-prescription sleep aid can help them fall asleep faster, but only by about 10 minutes. So who cares? A careful use of statistics may convince us that there's something going on, but it may not be big enough to care about. With a large enough study, you might show that a new cancer treatment extends patients' lives by 2 weeks. So what? 2 weeks, unless you're the patient or the family member, 2 weeks is just not enough to upend medical practice and try to convince everybody to change to a new treatment, not to increase by 2 weeks. Rather, you should go back and look for better cancer treatments. So I strongly, strongly encourage you to watch the first video in the series, Against All Odds, Inside Statistics. You can just Google it, or the website is here. And in general, in this course, especially when there are things that you struggle with, I encourage you to Google and look for YouTube videos or other sources and just get information from as many places as you can in order to see other points of view. But I especially recommend this series, Against All Odds. I strongly urge you to watch at least a couple of these short videos and see if they help you in the course and if you like them. And if you do, then you'll keep watching them.